Let's begin with the various ways cells can be connected. When you put two cells in a flashlight, you are really connecting two voltage sources in series. Even though we commonly say that we are putting batteries in a flashlight, we are actually putting cells in a flashlight. And since a battery is two or more cells, we actually have only one battery powering this flashlight. In this stereo radio, just as with the flashlight before, we are connecting cells end to end, positive to negative, in series. This is known as a series aiding configuration. In short, we might say that series aiding is when cells are connected in a single string or end to end and with the positive of one cell connected to the negative of the next. The open ends form the positive and negative terminals of the battery. Of course, it may not always seem that we are connecting cells end to end in series, since the cells themselves don't always touch. In these cases, it is the wiring of the cell holder that is configured in series. The cells themselves, then, are still connected in series, even though they might not look like they are. The reason we connect cells together in the first place, as in this solar battery, is because a single cell alone often cannot provide enough voltage to power the devices we wish to operate. By connecting cells together in series, we create a single current path through the cells and are able to increase the voltage because the individual cell voltages are additive. That is to say, the voltage of one cell adds to the voltage of the previous cell. Connecting another cell adds still more voltage. Since the individual voltage of each of these cells is 1.5 volts, the total voltage of these three cells working together as a unit is therefore 4.5 volts. The two general rules regarding series aiding arrangements then are, first, the total EMF equals the sum of the EMFs, or V sub t equals V sub 1 plus V sub 2 and so on to V sub n, representing all the series aiding connected cells. And second, since the individual cells are arranged to form a single current path, the current is the same in all cells and in the external circuit. This is shown as I sub t equals I sub 1 equals I sub 2 equals I sub n in equation form. Let's see what increased voltage means in the case of a simple circuit. As you can see, with only one voltage cell connected to this circuit, the lamp glows dimly. What will happen if another cell is connected in series in the circuit? Will the lamp glow more brightly or for a longer period of time? Let's see. As you can see, the added voltage increases the brightness of the lamp. Does that mean that the current can continue to flow for a longer period of time? No. Voltage sources connected in series do not increase the current capacity of a circuit. A voltage source can be thought of as the push or energy that is given to electrons to enable them to do work. When the second cell was connected in series with the first, the single current path continued through the second cell, where the same number of electrons simply gained more push or energy. This enabled them to do more work in the lamp, which we detect as increased brightness. If we connect yet another cell, the electrons will flow with still more energy, causing the lamp to glow even more brightly. Each successive cell that is added increases the total voltage, making the lamp glow more brightly, since there is more push or energy on the electrons flowing through the lamp. You can prove this yourself with any flashlight that is growing dim. Why is it growing dim? Because the cells are wearing down. That is to say, the voltage in the cells is decreasing. Thus, when you install fresh cells, you increase the voltage relative to the voltage in the old cells, and the bulb glows brightly again. Another way to think of the additive effect of voltage sources that are connected in series is by thinking of the 1.5 volt voltage sources as individual water pumps. Just as the first water pump raises water to the first level or potential, so a chemical cell pumps electricity to a certain level or potential, 1.5 volts, the next to a higher potential, 3 volts, and the third to an even higher level or potential, 4.5 volts. The total EMF increases with the addition of each individual EMF or voltage source. In this case, the total EMF adds up to 4.5 volts. The current capacity remains the same because the individual pumps share the same single water pipe or current path. Now, what would happen if cells were reversed? If cells are connected so the negative or positive terminal of one is connected to the same terminal of the next, this is the opposite of a series aiding connection and is known as a series opposing connection. The repulsion of negative against negative and positive against positive in a series opposing connection causes the series opposing cell to cancel the voltage of an adjacent cell. A series opposing connection, of course, is normally an accident and has little practical value. In this case, the flashlight doesn't work at all because the two cells have canceled each other out completely. And since there is no voltage, there can be no current. Thus, the flashlight does not light. But a series opposing connection does not necessarily have to result in no voltage or current. Let's look at our lamp circuit again, the one where we increase the voltage to 4.5 volts. What happens if we reverse one of the 1.5 volt cells to produce a series opposing arrangement? Will the lamp still light? As you can see, the answer is yes. Now, the lamp can only be glowing if current is flowing, and current can only flow if there is voltage. So we know there must be voltage, but how much? Well, since each cell has an EMF of 1.5 volts, and since two of the cells are in series opposing arrangement and are therefore canceling each other out, that leaves only one cell whose voltage is 1.5 volts. Thus, only 1.5 volts is causing this lamp to glow, which is why it is so dim.